Hello and welcome back. This is week 5 of ESTEP. This week we are going to be focusing on metamorphic rocks and metamorphic processes or metamorphism. So let me go to the screen. Just need to. Okay, so we'll get back to these toilet seats later. They're there for a reason. So this week we're just going to take a look back at the rock cycle to see where everything fits in, and particularly important for metamorphic rocks, as with igneous rocks, how do they fit in with plate tectonics? And then we move into some metamorphic rock concepts. So let's revisit the rock cycle. So where are metamorphic rocks? They are down here. And as you will remember from before, they form as a result of increases in temperature and pressure. And geologists often use the term burial for rocks that have been pushed down to whatever depths they've been pushed down to. We talk about burial, and that just means they've been pushed down to somewhere below where they formed. So here we are in metamorphic rocks. And what I want you to remember is that we can make metamorphic rocks from igneous rock, from sedimentary rock, and then there's also metamorphic rocks that get made from pre-existing metamorphic rocks, maybe during the same metamorphic event, or maybe there's some metamorphic rocks that are formed and then they get re-metamorphosed at even higher temperatures and pressures. And that gets awfully complicated. What I want you to remember, the bottom point here, is that all this happens in the solid state. The rock never actually melts. If we have melting, it transitions to being magma. Now, there is a gray area right in between where parts of some rocks start to melt. We'll talk about that a bit later. So you are reminded about where they fit in. Now I want you to just think back to plate tectonics and think about where rocks get heated and squished. So in this diagram down here, it's trying to capture the essential plate boundaries. So right in here, we've got a divergent plate boundary. Remember, this is a cross section, a vertical slice through the lithosphere, or the crust up here. So here we have a divergent plate boundary. You can see the arrows pointing away from it. New seafloor is made right here. And because of that molten material that is rising up, we've got high heat flow here. And so a lot of the rock that is formed here actually gets weakly metamorphosed. We call that seafloor metamorphism. So the igneous rock, the basalt or gabbro that forms here may get weakly metamorphosed. Then I'm going to move over to the right-hand side. Here we've got a plate that's being subducted. It is being pushed down or diving down beneath this piece of continent here. So we've got a convergent plate boundary, and everything that is getting pushed down that subduction zone is impacted by what we call subduction zone metamorphism. So it's being heated up. Often there's water that gets involved in things because of all the goopy sediments that also get pushed down. Now we're going to move on to this piece of continent here. So what I want you to notice is that we have a magma chamber right here. That's because we've got molten material that's being generated at the base of the crust where this slab is being subducted, and it's forcing material here to melt and melt the crust above it, which fills this magma chamber. So anywhere that's near that magma chamber will get metamorphosed, and that's called contact metamorphism. Contact metamorphism is mostly about just being heated. And yes, there's a little bit of squishing, but it's mostly heating. Now, anywhere in this area, they've picked out an oval-shaped area E here, but it really could be anywhere in the crust, this brown area in here. We'll get what's called regional metamorphism. So basically, stuff that starts out as sediment or maybe volcanic material gets buried, heated up, and if it gets pushed down far enough by all the squishing that is taking place in this bit of crust here, because it's close to the subduction zone, that will be affected by regional metamorphism. So we've looked at one type of convergent plate boundary here. We've got a ocean continent plate boundary. Now we're going to shift over here. And in this case, we've got two pieces of continent that have collided. Now, when they collide, the actual process of subduction gets stopped for a bunch of reasons. But what happens here, and the best example of this is the Himalayas. This is India crashing into Asia here, and these peaks would be the Himalayan peaks. And that convergent boundary, which is now a continent-continent collision, results in all this crust being squidged together, and it gets heated up, and that produces regional metamorphism, not unlike what's happening over here on the right. So we've now got basically 1, 2, 3, and I'm calling A and E pretty much the same thing. So we've got 4 main situations where one can get metamorphism. So when we're thinking about metamorphic rocks, I want you to just focus on the text over here first. What's really important is whatever the starting material was, because that controls the type of metamorphic rock that will form. And there's a fancy word we use for the starting material. It'll be the protolith. And that's going to control the type of rock, the type of metamorphic rock that gets made. So just here, make a mental list of all the igneous and sedimentary rocks you know. What has the potential to be metamorphosed? Now we can take a shift over to the right to look at this diagram here. It's effectively a cross-section, a vertical slice. And in red, I've highlighted some different protoliths. We're just going to focus on the left-hand side of the diagram at the moment. So we've got here highlighted a mafic and ultramafic igneous rocks, and then some of our favorite sedimentary rocks, conglomerates, sandstones, shales, and limestones. And What hasn't been included here are all sorts of other intrusive and extrusive rocks. We'll come back to this diagram later. We're just focusing on the starting material at the moment. Okay, so the next big deal about metamorphic rocks is because they're being squished, that squishing or the increase in pressure produces what we call metamorphic fabrics. It's kind of like metamorphic layering. And there are all sorts of terms that get used, and people use them in all sorts of different ways. So fabric is a very general term. Sometimes people substitute foliation for fabric. I'm not so keen on that because I think foliation implies more of a distinct breaking, kind of like the word cleavage. So you encountered the word cleavage when we looked at minerals. Now we're thinking about the word cleavage in terms of a metamorphic fabric. So that's a different thing to the use of the word cleavage in minerals. So you could say a metamorphic cleavage, but if you're talking about metamorphic rocks, then it's metamorphic cleavage. Other words for the fabrics, there's a word schistosity and then a word gneiss-osity. So cleavage, schistosity, and gneiss-osity. And then there are some metamorphic rocks that don't have any fabric at all. So over in the image on the right, this one here is an example of cleavage. And so effectively, the rock will have a tendency to break in layers that may or may not be parallel to any original bedding if it was once a sedimentary rock. We go through a rock here, the one that I'm got the cursor on right now, that is a schist. That's an example of schistosity. It's a bit hard to see the layering well with the orientation we're looking at it in. But then down here, we've got a gneiss, or we've got an example of gneiss-osity, which is essentially banding with dark and light layers. Some people use the term mineral segregation because they segregate into light mineral layers and dark mineral layers. Now, hang on. I'm going to go back a moment. So we've talked generally about fabrics here. Just these fabrics exist. Now, don't panic. Over on the far left is a list of the metamorphic rocks in your rock and mineral kit. So you know what they are, and by the end of this, I'm hoping you should be able to identify them. Here in blue, I'm highlighting the key metamorphic rocks: slate, phyllite, which was that intermediate one between the sample with the cleavage and the sample with the schistosity. So slate, phyllite, schist, and gneiss. So here, this is spelt G-N-E-I-S-S, but it's pronounced gneiss. Think Minnesota gneiss. And then there's marble and quartzite. And a reminder down here that the parent rock or protolith is what's most important. Now, let's move over to this table. I don't want you to get alarmed by this. So in the first column on the left, we have our metamorphic rock name. So slate, phyllite, schist, gneiss. So yes, they are They will likely, or they may have different protoliths, but another important thing here is if a rock gets increasingly metamorphosed, in other words, more squishing, more heating, it can progress from being a slate to a phyllite to a schist to a gneiss. That's why it says increasing metamorphism next to that arrow. The word migmatite is used for partially melted rock, and that's that awkward area in between metamorphic rock and magma. Migmatites may be associated with gneisses. That's if the gneiss gets heated up enough to start melting. We aren't going to worry about mylanites or metaconglomerates. We're going to go down here to marble and quartzite here. These are really interesting metamorphic rocks because they generally, I'm saying generally, don't have a metamorphic fabric. And the reason for that is, let's just move over to the right. The marble is made up of limestone, or maybe dolostone, and the quartzite is made up of or derived from a quartz sandstone. So they started out being just one mineral. And one of the things that helps a metamorphic fabric develop is having a range of minerals. And then when the rock's metamorphosed, those different minerals will reorganize, the elements all move around, new minerals grow, and the new minerals effectively define the layering or the foliation. So here you'll see, as we move over to the next column, which is the word texture, slate, phyllite, schist, and gneiss are all foliated. But then we get down here into non-foliated rocks. That it includes marble and quartzite. And there's, hornfels is a rock that has been contact metamorphosed or metamorphosed near a magma chamber. Anthracite is coal. So we've got texture, and they've tried to put a visual texture image in here. Next column is the grain size. So if something's weakly metamorphosed, it probably won't have its grain size changed that much. A slate is made from shale, mudstone, or siltstone. So it's made from really fine minerals to start with. And what happens in the making of the slate is that those minerals are just recrystallized. And the difference between a slate and a shale is that a slate has, if you sort of flick your finger against it, it has a ping and it breaks into layers a lot more easily. So here's information on the overall grain size, and there's some useful comments here. And over on the right, it has the likely or most likely parent rock. In other words, protolith. So that's an important table to just get your brain around. So now let's go back to this image. We're thinking about the naming of metamorphic rocks again. So these terms, shale, slate, phyllite, schist, and gneiss, are represented by each of these rocks. And they're the essential metamorphic rock name. But something else that happens is we often qualify this with some word that tells us something about a distinctive mineral that is in the rock, particularly if we're dealing with a schist, for example. there's another term that gets used, and this is metamorphic grade. That's about how metamorphosed a rock is. We'll come to this soon. So let's look at a little bit more closely at some of these. Here is a schist, and we're not looking at the layering, we're looking down on a flat surface. This is a muscovite schist. Remember I said sometimes the word schist gets qualified? In this case, it's been qualified by the word muscovite. You've looked at muscovite when we looked at minerals. So what we're looking at here are many layers of muscovite in with a bunch of other minerals, and they create this schistosity, the layering. In the lower one, there's a mineral we haven't actually looked at, garnet. It's a purple-brown mineral in many cases. There are a bunch of different colors, but we'll go with purple-brown. It's most common. It's a garnet muscovite schist. So what you can see is these garnets have grown. Those are metamorphic minerals. And if we turn this on edge, then we'd see that this was sort of breaking apart in many ways, in a way that's very similar to the muscovite in your rock and mineral. So a reminder, schist is layers of minerals, and typically a schist will include layers of mica, the muscovite or biotite. Sometimes it will be amphibole group minerals. That would be a very dark colored schist. That would typically be derived from something like a basalt or a gabbro. So schist typically develops from a lower grade metamorphic rock, something like a phyllite, maybe a metasandstone or a metasiltstone, or basalts. So that's schists. And then, shale, slate, and phyllite. This is where it starts to get a tad messy. So over on the left, the word shale, which gets used for sedimentary rocks that are really fine-grained, is kind of a betwixt and between term. So, you know, there's some kind of layering, and it breaks apart usually along natural bedding planes, sedimentary layers, but it isn't metamorphosed enough to be called a slate. So this gets a bit messy, and people use the word shale in a variety of different ways. I usually think of it as, okay, it's not a siltstone or mudstone, it's just started to break off in layers. Whereas once you get to a slate, and here we have some roofing slates, you know, it is fine-grained, definitely foliated. And the slight sheen one often sees on it is a result of those fine-grained clay minerals recrystallizing. There's really fine-grained micas in it. Then if we upgrade that slate and maybe bend or fold it a tiny bit, the mica, tiny mica minerals in it that you can't see with your naked eye, but they tend to reflect light. So as you move it around, it sort of has a slightly shiny, wavy appearance. So now, okay, you may have wondered about the toilet seats. So remember we talked about non-foliated rocks when we used marble and quartzite as an example. I was Googling marble, and where else but on an Italian home improvement website, they had a whole bunch of marble toilet seats. So yes, marble typically isn't foliated, And I've told you, oh, it's all made of calcium carbonate or limestone. Well, yeah, but this is all marble. Marble can be many different colors. It's all made from calcareous ooze that collects on the seafloor. There can often be impurities in that sediment, and those impurities will lend the sedimentary rock that these marble toilet seats started as different colors. And then when they get metamorphosed, they will retain that color variation. And you can see that the sort of, it does look as though they've been broken up or brecciated a little bit. That's very much the nature of marble. It's can be quite complex, but here it's just one mineral. It's calcite. It just recrystallizes to make marble. And then quartzite. Remember, quartzite is made from a quartz sandstone. Where do we have quartzite in Minnesota? The Sioux quartzite in southwestern Minnesota. It is absolutely beautifully exposed at Pipestone National Monument and at Jeffers petroglyphs. Now, the quartzite here is quite pink in color. You can also see amazing sedimentary structures. There's a really nice trail there. I really encourage you to take a visit. And here we have 3 examples of quartzite. There's a wide range of colors, and that's just a consequence of there being, you know, some impurities. The one on the upper left is, I think, from Baraboo, Wisconsin. Often the Baraboo quartzite is somewhere in between these two. It's almost a slightly blue-gray color. But quartzites can range in color, and they are just recrystallized quartz. Now, don't panic about this diagram. We are going to walk through it in a moment. So, I've said that minerals, new minerals, grow in metamorphic rocks. And here there's some important text. Let's look at that first. The minerals that grow in a rock, in a metamorphic rock, are a record of the temperature and pressure that the rock experienced. And that's because every mineral has what we call a stability field, pressures and temperatures that it can survive at. If the conditions move out of that, then the mineral is not likely to survive. Now, based on the variety of minerals that grow under different conditions, we can divide metamorphic rocks up into groups that get called metamorphic facies. That's this funky word here, facies. Some people say facies. Doesn't matter. If you're talking to a geologist, they will know what you mean. Now, first, let's take a look at the axes on this graph. So up here, I always think of this as being Earth's surface, right here. So on the y-axis, we're going down in depth. This is the same as increasing pressure. Often on a diagram of metamorphic facies, there will be pressure shown over on the right-hand side. I went with just looking at depth. Now, on the x-axis, going from left towards right, we have the temperature in degrees Celsius. So it's increasing, going from the left to the right. Now, there are lots of lines and lots of areas. First, I want to just say something about these different colored areas. They represent different metamorphic facies. So this yellow area represents the stability field for what we call zeolite facies. I don't usually use the word clay. I don't know why that's in here. In this blue area, that is the stability field, the temperature and pressure range at which blue schist facies minerals are stable. And there's a bunch of different minerals that will all form together that are characteristic of each facies. Once you get really deep and a lot hotter, we have eclogites. In the middle here, and one of the most common metamorphic facies is green schists. In Minnesota, we have a lot of green stones, and the definition of that term is a can of worms. But at the moment, just think of green stones as being basaltic, mostly rocks that have been metamorphosed to green schist facies. And the boundaries of this gray-green area mark the sort of limits of pressure and temperature. It covers a wide range of temperatures and pressures. And most of the minerals, no surprise, are minerals that are slightly green in color. If we increase in temperature, and we're somewhere between, this is supposed to be 10, the one's missing from it, somewhere between maybe 8 kilometers below the surface and 35, we get into amphibolite facies. Surprise, surprise, or not, a lot of amphibole group minerals are present in amphibolite facies. Remember amphibole or hornblende? That was that dark mineral that looked a lot like pyroxene. And then once we move over to the right, we get into rocks that are granulite facies. So deep, well, range from deep to maybe 8 kilometers, but really high temperatures. And then here we've got rocks that form at relatively low depths, less than 5 kilometers, but high heat, so hornfels. These are rocks that form near magma chambers when you've just got a big pulse of heat coming in, but not necessarily a lot of squishing. Now, there are some other lines here. This blue one here shows the trajectory of a subducting plate. So rocks that get shoved down a subduction zone will follow this line right here. So that's when you can produce these blue schists and eclogites. Let's look at this green line. This is what is identified here as the typical geothermal gradient. So that's the classic rate at which temperature and pressure changes as you go down into the earth. So this is your classic progression from a slate through a phyllite into a schist, maybe into a gneiss. Oh, and look here, we're starting to get migmatites. Remember, these are when a rock starts to have areas that are melting. And you'll notice that that coincides with this red dashed line here. It says wet granite melts. And when it says wet granite, it just means that there is a bit of water in it. That always means that it melts more easily. The other line here, this yellow line, it says volcanic region temperature gradient. So if we've got an area near a volcanic arc an island arc, or a chain of volcanoes on a continent, a continental arc. Then this is the trajectory as you go down, the geothermal gradient in one of those regions. So the diagram wasn't quite that bad, was it? So that's all very sort of organizational. It's about how we think about rocks. Now, I want you to just go back to thinking about plate tectonics. What we just looked at kind of touched on the areas that we were considering for where metamorphism takes place. So there's contact metamorphism, right here near a magma chamber. Remember the seafloor metamorphism, subduction zone metamorphism, and regional metamorphism in a piece of continent or a continental arc area or a continent-continent collision zone. So now we can look back at our cross-section, our plate tectonic simple model, and you can match up what's happening up here with this facies diagram. So I encourage you to pause the video here and do that. And if I'm got this right, the letters on the diagrams should match. All right, so now we're going to go to a slightly different type of cross-section. I've shown you this before when we were starting to think about protolith. And now we're going to look at the rest of this diagram. So over on the left, we've got our sedimentary rocks. And essentially what we're saying here is just the sort of natural squishing or confining pressure is what turns the sediments into rocks, sedimentary and low-grade metamorphic rocks. Now, this is kind of a contrived cross-section. What it's trying to show is things get deeper and they also get closer to heat. And it's showing how shale will be metamorphosed, become slate, phyllite, schist, and gneiss. That's sort of your classic progression. But here it brings in limestone and marble, and it's also showing how often that marble becomes more deformed. That means folded as it's being more and more metamorphosed. So, and they've also just divided these rocks up. They've added directed pressure or differential stress, just meaning, okay, we've got a whole bunch of extra squishing taking place that impacts the formation of these rocks. And then right in around this granite intrusion, that granite came in after these rocks formed, everything is really heated up. That is contact metamorphism, or this Hornfels. So there are a couple of other terms. If you think back to the beginning, I mentioned the phrase grade gets used, and people say low grade, intermediate grade metamorphism, high grade metamorphism. How does this fit in with what we've learned so far? Well, up in the top here is a simple metamorphic facies diagram, and you'll notice that this one has pressure on the y-axis here and depth over on the right, but still got temperature going from left to right, and you can match the scales on the top and the bottom. So here, what we've got is a diagram that captures what gets called low grade, intermediate grade, and high grade metamorphism. So rocks that aren't really metamorphic, and then blue schists are in a class of their own, really. There's low grade, intermediate grade, and high grade. And what I encourage you to do is compare these two graphs and see where they fit. How they match up. You may want to pause the video here. Whew. Now, here are some more graphs. One thing people always wonder, well, how hot does it actually get? So to understand that, we have a term we use, the geothermal gradient. This is effectively just how temperature increases with depth. So we've got a diagram, not unlike our FASES diagram. It has depth on the y-axis and temperature on the x-axis. And what's useful is they've added in your average lithosphere thickness here. So that's your crust and uppermost mantle. And then it goes down to the asthenosphere. And what's important is this black line represents the geothermal gradient. So it's how temperature changes with depth as you go into the earth. And what you'll notice is it increases relatively rapidly as you go through the lithosphere down to about just over 100 kilometers. And then the temperature does not increase as much below that as you go down. And here we're looking at the bigger picture for the geothermal gradient as you go all the way to the inner core. Now, how does this mesh with what the temperatures are actually like at a subduction zone? What I suggest again that you may want to pause the video here and look closely at this diagram. What you'll notice is that temperatures, you have to go a little bit deeper to get to 300 degrees. That's this one, or 600. Then you have to go, if you're in the continental crust here, near a magma chamber or a series of igneous intrusions, because that's what magma chambers become. The reason for this depression, if you like, of the temperature is just because we're bringing some water down in here and it just has to go deeper to get hotter. So what about Minnesota metamorphic rocks? Minnesota's most famous metamorphic rock is the Morton gneiss. It was once thought to be the oldest rock in the world, 3.8 billion years old. We now know there are older rocks in Canada, Greenland, and Australia. Morton gneiss is often used for facing stone on important buildings. And if it is present as facing stone, it's often been beautifully polished. A lot of the buildings in downtown St. Paul use Morton gneiss, and it's found in many town halls and other really important local buildings. This is a wonderful sign that no longer exists in Morton. Don't take Morton for granite. It's nice. Anyway, and I put this in here to remind you, where are we on the metamorphic facies diagram? If we're dealing with a gneiss, we're somewhere in between an amphibolite and a granulite. Now, most gneisses are made from a variety of igneous rocks. And because the quartz-rich igneous rocks melt at lower temperatures, they will often start to melt and you'll get zones of migmatite in a gneiss. Okay, so that's all I have for you on metamorphic rocks. Read the textbook and do the various assignments and have a good week. Thank you.